Good morning, everyone. It's the same lesson you were supposed to have done yesterday.
I'm tired. So you're like teaching the whole lesson over again?
I'm going to go over parts of it that I think people may have struggled with.
Good.
Not necessarily the entire lesson.
So I'm just gonna my entire lesson.
Yeah, I need to get a whole new notebook.
I don't have just fine.
Whenever you guys are ready.
I mean, it doesn't just go away automatically. But unfortunately, no. I'm still very sorry.
Does this mean we're ready now? Okay. So hopefully you all at least looked at the notes from yesterday. I can't promise that you did because I know you, but I'm hopeful you all at least looked at it and attempted the homework. We actually did. That was really fun. I don't know what I was going to say now. I lost it. Girls, I will remove you from each other if I have to. Okay. So we're going to go over the notes. I'm probably just going to go through them all because they're really not that long. However, I'm going to focus on the examples that I gave you homework problems over because that's what I'm going to give you on the quiz and then on the final exam. So you will not have a test over this. I don't know why. This will be tested technically on the final exam. So you will have a quiz over this, but no formal test.
For real?
For real.
Wow.
Before the final exam, no formal test.
Wow.
So exponential functions are functions that have a constant as a base and a variable in the exponent. So for example, 2 to the x is an exponential function. I have some number as my base and my variable is present in my exponent. Another example could be, I don't know, -15 to the 3x power. The variable is still in the exponent, and I still have a number as a base. Anytime you have a variable in the exponent and a number as a base, it is an exponential function. This also applies if we have a base e. E is still a number. We just use e to represent it because it's an irrational number, just like we use the pi symbol to represent pi. Pi is still just a number. Okay, so this is still an exponential function. I have a numerical base and an variable in the exponent. Okay. So some interesting things about exponential functions, they are one-to-one, which means the only way for 2 exponential functions to be equal is if the variable is equal on them as well. So for example, or actually let's write the theorem. So if I have 2 variables that are not equal to each other, then any base raised to those variables are also not going to be equal to each other. Coming from the other direction, if any base raised to those exponents are equal to each other, that means those exponents themselves must have also been equal to each other.
Nice.
Okay, so if the variable isn't equal, then any base raised to those variables is also not going to be equal. On the contrary, if any base raised to exponents is equal to each other, their exponents must have also been equal. And by exponents, I mean variables as well. So of course, we're going to do an example of this because I did put this on your homework. So the example I would like to use is if I have 7 to the 3x equal to 7 to the 2x plus 5. The first thing I need to check is, are my bases the same? Yes or no?
Yeah.
If they are not the same, I need to see if I can make them the same. Lucky for me, 7 equals 7. So those are exactly the same, which means I can just bring their exponents down and set those equal to each other. So this means I'm going to have 3x equals 2x plus 5, which makes it very easy to solve for x. Right? I'm just going to subtract 2x over. When I do, I'm left with 1x equals 5. So the solution to this equation is that the variable x has to equal 5 in order for those two to be equal to each other. Anybody confused by what I did there? Does that make sense? Okay, so what if I did another example? Let's say this time I have 3 to the power of 5x minus 8 equals 9 to the power of x plus 2. And I would like to solve for x. What's the first question I need to ask myself? Are what the same?
Base.
Are those bases the same? No. If you answered no, we have to ask ourselves, can I make them the same? Yes, what can I do to which one, Marissa? Okay, so I don't actually want to make this one bigger. My goal is actually to make them smaller until they're the same. So I can't make this one smaller because 3 is prime. Can I make 9 smaller and turn it into a base of 3? Yes, because 9 is what?
Square.
3 squared. So all I have to do is replace this 9 with 3 to the second power. When I do that, I get 3 to the 5x minus 8 equals 3 squared to the x plus 2, right?
Yeah.
Now I have a base of 3 on each of them, so I'm pretty much good to go. But I also notice I have 2 layers of exponents here, and that gets really, really confusing. So it's also important to note that that can be rewritten as 3 to the 2 times the variable that was already there, the exponent, sorry, that was already there. So I just took that 3 squared, I kept the base 3, and I multiplied the current exponent by that squared. So when I do that, I end up with 2x plus 4 as the exponent on the second one. Because 2 times x is 2x, 2 times 2 is 4. My bases are the same, and I have single layered exponents, which means I can just bring the exponents down and set them equal to each other. And then I solve for x. To do that, I subtract 2x from each side, which leaves me with 3x on the left. I add the 8 over, and I get 12 on the right-hand side. To get x by itself, I need to do what next? Divide by 3. When I do, I get what? So the solution to this equation is x equals 4. Questions, concerns, or issues with that? There will absolutely be one of these on the quiz in the final exam, just so you know. It's a really good question. So what I'd like to do next, since we already looked at exponential equations, is graphing exponential functions. So for this example, I would like to graph. Let's do 3 halves x. This is an exponential function because my base is 3 halves, which is a number, and then my variable is present in the exponent. Just like with any other graph or any other function, how do I graph this? Do I just make something up, or do I use something?
Make it up.
Make it up. No. What do I use?
You can use a table.
I can use a table, which means I'm just going to plug in x values and get the accompanying y values and plot those points, correct?
Is there a way to graph that on the graph?
Absolutely. She ain't pretty, but it works. So when we are doing an exponential function like this, it's important to note the general shape of all basic exponential functions. Either it grows, so it looks something like this. That's an exponential growth graph. Or it will decay as it gets farther to the right, and that's an exponential decay graph. So when I'm plotting this, am I just going to pick positive x values, or do I need an equal distribution of negatives and positives?
Equal.
Equal, because I can clearly see in both of these generic graphs that I have almost the same number of points on the left-hand side as I do on the right to identify the shape. So I'm going to need negatives and positives here. Just as a generic, I like to start at -2 or -3. -3 to 3 or -2 to 2 are usually pretty decent. So I'm going to do -2, -1, 0, 1, 2, and 3. Just to identify the shape. If I need to plot more points, I easily can. So then all I really have to do is take each of these and plug them into the exponent, right? Because that's where my variable's at. Ray, what's going to happen if I put a -2 where that x is? Say that again, huh? Okay, so she notices that when I put a -2 where that exponent is, I have a negative exponent, which means my exponential rules apply here. Whenever we have a negative exponent, that means I do what with the entire fraction? We flip it over. So this becomes +2/3 to the +2 power. So once I flip it, because it became negative, I still have to apply that exponent. Anybody confused by how I did that? Okay, so then from here, I just apply the square to each the numerator and the denominator, and I get my answer. 2 squared is 4, 3 squared is 9. So the answer I get for plugging a -2 into the variable is 4/9, which comes out to be roughly 0.4. So if you want to, you can actually start the graph now, since we do have a point. You don't have to, you could wait till the end if you preferred. So I'm going to go 0.4 approximately. And then I'm going to plug in -1 because that's the next value that I identified. So I plug in -1, which leaves me with 3 halves to the -1 power. Anytime I have a negative exponent on the outside and a fraction on the inside, what do I have to do? Flip it. When I do, it becomes 2/3 to the +1 power, which is just what? So the answer for that one is 2/3. Again, I can go ahead and plot that point. That's roughly 0.66.
Oh.
And then we move on to the 0. What happens when I have 0 as an exponent?
Wow.
The answer is just 1. So at 0, my y value is 1. I repeat the same thing with 1, 2, and 3 in my positive exponents. I know 3 halves to the 1 power is just 3 halves. I know 3 halves squared is just 3 squared over 2 squared, which is 9/4. And I know 3 halves to the 3rd power is just 3 cubed over 2 cubed, which is 27/8. I go ahead and I plot all of these points. I did not do that right. There we go. That's much better. And then I can go ahead and draw the graph, correct? Is this an exponential growth or decay graph?
Definitely decay.
As I move to the right, did the values get larger or smaller? Gunner, don't do it. As I move to the right, everyone except Gunner, did my y values get larger or smaller? which means it grew, which makes this a growth graph. What? I know, magical. Okay. Anybody confused by how I graphed that? Shall we do another?
Yes.
Yes. Yes, we shall.
You want to do the homework? Is that what you want?
You don't have homework today if you already did the homework, so that's already a plus. Okay, so now I would like to graph 1/2 x. Just like before, I'm going to go ahead and use, this time let's do -3 to 3 since I did -2 to 3 last time. You suppose, right?
If you're gonna do it, might as well
Yeah.
do it.
That's your 1.
Yeah, this week.
Okay. Okie doke. When I take 1/2 to the -3 power, what's the first thing that's going to happen?
Who is this?
It's going to flip, and 1/2 becomes 2, or 2 over 1, which is just the whole number 2. And then we raise that 2 to the +3 power, because once I flip it, the negative goes away. 2 cubed is 8. So in case, I guess, you need the visual, this becomes the fraction flipped to the +3 power, 2 cubed is 8. I do the same thing with the -2. 1/2 to the -2 flips and becomes 2 to the 2, which is 4. 1/2 to the -1 flips and becomes 2 to the 1, which is just 2. 1/2 to the 0 becomes what? 1/2 to the 1 is 1/2. 1/2 squared is 1 squared over 2 squared, which is 1/4. And 1/2 cubed becomes 1 cubed over 2 cubed, which is 1 over 8. Once I have all of my y values, I go ahead and I plot this. Was this an exponential growth or decay?
Growth.
Decay, because as I went right, my graph got lower and lower and lower. So there's actually a way of figuring out whether you're going to have a growth or a decay based off of our base value. I wanted to do each of these examples, so maybe you guys can come up with it on your own.
I know it.
You do?
Definitely not because it's in my notes.
Okay. So let's just take a look. What was my base value on my growth graph? 3/2. What was my base value on my decay graph? 1/2. So couldn't we generalize that any base greater than 1 is going to give us a growth? Well, any base between 0 and 1 is going to give us a decay. Yes, we can, because that's
Wait,
absolutely
say
right.
that again. Say that one more time. After you do.
Okay, so when I have the exponential function a to the x, if that base a is greater than 1, it is a growth function, which means as I go farther to the right, my y values are going to get larger. Any base value between 0 and 1, so a fraction that's less than 1, it will be a decay graph, which means as I go to the right, my y values are going to go down or get smaller. This should definitely definitely somewhere in your notes. Anybody confused by any of that? Does that make sense? Okay, so what if we don't have just a growth or a decay? What if we end up with a bell-shaped graph? For example, 2 to the negative x squared. We end up with a bell-shaped graph whenever we are squaring our variable, which is in the exponent, or taking it to a 4th power or a 6th power. So anytime it's taken to an even power, we're going to end up with some sort of bell shape. I know this looks a little bit confusing because I have an exponent on an exponent. Sometimes it's easier to remember that that's all one entity, and I'm taking 2 to whatever that answer comes out to be. So I like to use parentheses so I remember all kind of groups together. However, I don't like the way this is written. Why not? I've got a negative in my exponent. We really don't like that. So how could I rewrite this so that the negative was no longer in that exponent? I can move that whole thing down to the denominator, which means this is the same as 1 over 2 to the positive x squared. The 2 moved with it because the negative variable was in the exponent, which means the base also had to move. And then from here, I would graph her just like I graphed the previous one. We can go negative 2 to positive 2. We plug it in just like normal, and then we graph our answer. So what happens if I plug negative 2 into that variable?
Get back.
I'm going to get what?
4.
Because negative 2 squared is 4, and then I get 2 to the 4th, which is what?
16.
That 16, however, is in the denominator. Gunnar, you're not allowed to talk anymore.
Okay.
So I get 1 over 16. Same thing happens when I plug negative 1 into that. Negative 1 squared is just 1. 2 to the 1 is 2. And then I have 1 over 2 because that existed in the denominator. 2 to the 0, however, becomes 1.
1.
And then 1 over 1 is just 1. Same thing happens when I plug positive 1 in. Positive 1 squared is still 1. 2 to the 1 is still 2. So I still end up with 1/2. When I plug positive 2 in, 2 squared is 4. 2 to the 4th is 16. 1 over 16 is still just 1 over 16. If I wanted to graph her then, she would look something like this.
Why do they call that a bell shape?
Because it is symmetric on both sides, just like a bell.
A hill can be the same way.
Very unlikely, actually.
That's true.
Possible. Actually. To have a perfectly symmetrical field of nature.
You could.
That's true.
God,
I guess that works too.
that's a really weird shaped muscle.
Have you guys ever heard of the bell-shaped curve?
Nah.
Okay, never mind. If we have time, we'll fit that in. That's a probability and statistics thing. Okay. Is anybody confused by graphing something that isn't exponential but doesn't necessarily follow our basic growth and decay models? Okay, so now all we have left are the application problems. And I think, yeah, I put 3 on your notes, and I think I only gave you 3 in the homework. So,
Well, 1 was a growth and 2 were application.
okay, well, awesome then. Oh, that's true. What is? Okay. So the first application problem I gave you is an exponential growth. This exponential growth model, I use bacteria to represent. Typically, when we're talking about exponential growth or decay, we're talking about it in the sense of populations. That's typically where you're going to see this, or revenue or value. Okay, so another example you see is like bank interest. That is an exponential function, as well as population growth and population decline. So you can use it to identify when species are going to go extinct, when they're going to surpass a certain population, all that kind of fun stuff. So this first application problem was done in the context of bacteria. So I said that if a sample has 1,000 bacteria to begin with, and the population doubles every day. Obviously, I'm cutting this out a little bit, so I would like to know what this model would look like. So unlike the previous problems, I don't have a function that I can actually plug things into, which means I need to start with what I know about day 1. What do I know about, well, technically we'll call her day 0, but what do I know about the initial start of this population? How many bacteria were there? 1,000, which means I still have an X and a Y table. For X0, which is when I started this population, there were 1,000 bacteria present. Then I use what I know about the change in population for the bacteria to find more XY pairs that I can then plot on the graph. So I know that my population doubles every single day. So if I started with 1,000 on day 0, how many will I have on day 1? 2,000. I just took 1,000 and I doubled it. If I have 2,000 on day 1, how many do I have on day 2? 4,000. I just took 2,000 and I doubled it. Which means on day 3, I will have how many? And then on day 4, I will have 16,000. We could keep going if we wanted to, but this is going to grow very quickly from here. So now I actually have enough information to graph this. I typically like to stay somewhere around 4 to 5 points. 5 is safer than 4 because it gives us a better accuracy in our model. So we have 5 points. I'm going to go ahead and I'm going to graph these. When I'm graphing this, do I need the entire coordinate plane? No, why not? Say that again, Becca.
They're all positive values.
Okay.
The X's and the Y's.
The X's and the Y's are all positive. I can't have a negative amount of time here. Okay, I'm starting at day 0 and I'm just working forward, so I don't have to worry about negative X values. It also turns out I didn't have any negative Y values. So I actually only need quadrant 1 to graph this model. Sometimes you might need 1 and 4. It just depends. So I'm going to count by thousands. Or actually, I'm going to count by probably 5,000. That'll be easier. Just so I can try and fit this all on the graph. So on day 0, I had 1,000. We'll say that's approximately right there. On day 1, I had 2,000. On day 2, I had 4,000. On day 3, I had 8,000. On day 4, I had 16,000. Clearly, this is growing the farther I get into this population growth. So once I have those 5 points, I can just draw it continuing to increase because that was the trend I was seeing in my other points. This actually allows me to roughly estimate what my population would have been on, say, day 1.5, right? I would go between 1 and 2, I'd follow it up and I'd say, hey, You know, it was probably roughly about 3,000 on day 1.5. I technically would not have known that if I wouldn't have plugged these values in and graphed it. We can actually also kind of build a function from this model. It doesn't guarantee it's going to be 100% accurate, but it does give us a starting point. This only works for the most part when we're talking about exponential growth models like this. So what we do is we start with our population that we started with, which was 1,000. And then our base identifies how our population is changing from day to day. So how is my population changing from day to day here? It doubles. So that means my base is going to be 2, because doubling is times 2. And then 2, we're going to say t is my exponent. It could also be x depending on what you wanted, for t number of days. So this would roughly approximate, roughly, I say that very loosely, what my population is doing after, say, like 5 or 10 days. Okay? I did not ask you to do this in the homework. It's just helpful to know. Application number 2, I believe, is a half-life problem. So it tells me that radioactive decay, that's usually when you're going to say half-life, it says the half-life of a polonium isotope is 140 days. I'm just going to pull out the important information here. If we started with 20 milligrams, I want to graph the model just like I did before. So the 2 pieces of information I needed here were how long my half-life was and how much I started with. Half-life means it's going to take 140 days for my starting population to be cut in half. It would also take another 140 days for that population to, again, be cut in half. So every 140 days, my population is directly half of whatever I started with. That's what half-life means here. Sometimes half-life is 10,000 years. Sometimes it's 2 hours. Okay, so make sure you're paying attention to whatever unit we're using for our half-life time. Okay, so on this one, we're going to start just like we did before. I'm going to have an XY table, and I'm just going to fill in X and Y pairs that I find from this information. I always like to know where I'm starting at time t equals 0, which is our initial place, our initial population. How much of this polonium did I start with? 20 milligrams. So my initial Y value is 20. I don't know what's happening on day 1 or day 2 or day 3 or day 4 or day 5. But I do know on day 140 that what I started with is cut in half. So the next X value I'm going to plug in is 140. What's going to be the population or the amount of polonium I have left at day 140? 10, because half of 20 is 10. Again, I don't know what's happening on day 141 or 142 or 143 or even 160. But I do know what's happening on day 280, right? Because that's 140 days past the last X value that I found. Which means that the amount of polonium I had at day 140 is now half on day 180, or 280, sorry. Half of 10 is 5. And I, of course, could keep this going if I wanted to. So day 420, I'm going to have 2.5 milligrams. And then day 560, I'm going to have 1.25. You could obviously keep going if you wanted to, but I have 5 points, so I'm good to go. Do I have to include any quadrant other than quadrant 1 on this coordinate plane? No, because I'm only dealing in positive time, and I can never have a negative amount of the polonium. The least I can have is 0, and I have not reached that yet. So I go ahead and I draw my graph. I'm going to go ahead and count by 100s down here on my x-axis. And then obviously 20 is gonna be my starting. And we'll go from there. So when I graph this on day 0, I started with 20 milligrams. So 0 and 20 is my first point. The next X value I had was 140. So day 140, the amount of polonium I had was 10. So I go to approximately where 140 is. I don't think I did very well, but that's okay. And I go to 10. And I keep repeating this until all of my values are on the graph. Once they're all approximately in their right place, I can go ahead and draw the graph that goes along with this. And then I'm finished.
Damn, it's fun.
Right?
Well, this.
It was hard.
Way
It was very
worse.
hard.
Sure it
Should
was.
lighten it up.
Sure it was. Okay, well, we only have one more application problem left, and I'm almost out of time, so it's perfect. So the last application problem is probably the one that is most applicable to your lives, and it is compound interest. I would like to note that just because we're talking about money doesn't mean it's always going to be a growth model. There are times where the value could decay or reduce over time, in which case it would be a decay model, okay? That's not just a growth model, it's just how we most often see it. So whenever I'm talking about compound interest, the key word here is the compound part of it, there's always one formula that I follow. This works also if you're talking about a decay model or where you're losing value over time. And this model is A equals P times 1 plus R over N to the N T power. P here is the principal amount that you started with. R is your interest rate as a decimal. N is the number of times per year you're taking this interest. And T is the number of years at which your interest is accruing. So the example I give you actually had 3 parts to it. We won't do all 3 parts. We might set them up, but they are solved in the notes. So on this specific problem, I said, suppose we started with $1,000 and I invested it at an interest rate of 9% compounded monthly. Find how much you'd have after 5 years, 10 years, and 15 years. As you're reading that, all you have to do is pull out this information. So from that story problem, how much money am I investing to begin with? 1,000. So that's my P value. What's my interest rate? 9%. Which we write as the decimal 0.09. So whenever you have a percent, we just take the decimal and move it 2 places to the left. And that's how I got 0.09. And this is usually the one that students mess up on the most. How many times per year am I taking the interest here? Okay, you need to pay attention to where it says when we're taking interest. So this said 9% compounded monthly. Monthly means every single month I'm taking the interest, and there are 12 months in a year. So that means my end value here is 12. And then T is going to vary depending on which of the years I'm plugging in. We're going to start with 5. Because that was the first place I had to solve it at. Once I have these 4 things, I just plug it into that equation. So then this becomes 1,000 times 1 plus 0.09 over 12, all to the 12 times 5 power. So I just plugged in P, R, N, and T. And then I would just plug this into my calculator, and I'd get my answer. And then I would go back to this equation For the second part, input a 10 where that 5 is. And then for the third part, I put a 15 where that 5 is. And then we're done. So this is a really good thing for you to practice on your own. Is anybody confused by anything that we've done so far? Does it make more sense for those of you who are maybe confused after looking at it yesterday? Okay. So again, your homework is technically due tonight at midnight. If you turned it in tomorrow, I probably wouldn't care. But tomorrow we are going to do a new lesson, just so you're aware. Anybody need extra help, extra questions, anything right now?
No, I do have a question.
Yes, ma'am.
So is this like if you like invest like the $1,000 and want to see how much money I'm gonna have down the line? That's
You
what
can
it
also
is?
use it to compare different accounts. So if I have like $10,000 that I want to invest and I'm looking at 3 different accounts, one of them could be 8% but is compounded yearly. One of them could be 5% but is compounded monthly. And then one of them could be, I don't know, like 11%. No, not 11, let's say 7. 7% but is compounded like bi-weekly. No, I don't want to say that. We'll say quarterly, which means 4 times a year.
Okay.
You could do this equation for each of those options and see which one's going to give you the most return after so many years that you're looking to invest it in.
Okay.
That's usually what this is used for. We also use it for like depreciation. So if I said that it decreased at 9%, this would become a minus.
Okay.
So it works the exact same way, but that's most commonly where it's used at, is to figure out which account or investment is the best for you.
Okay. Can you do it with like stocks and stuff like that?
Absolutely. You usually want to do it for something that's not going to change over time. So if it's like a really safe stock and that you know it's been gradually increasing or decreasing at the same percentage for so long, then it's usually better. If you have something that changes a lot, it's not going to work because it's not going to follow the same model all the time.
That makes sense. Oh my god.
Yeah, I like this because it's most applicable to people's lives.
Yeah.
I don't have to turn the homework because I didn't.
Is it online? Then you're good.